I took a day off and watched the opening ceremony of the Olympics in London, so you can guess when this lecture was given. If you think about it, churning this stuff out is pretty relentless, right? You have to study the material well enough to be able to lecture on it. You have to write it out fairly succinctly on the board. You then have to film it, and then you have to edit the film, cut it up, add titles and so forth. So process it, and then send it off, upload it to YouTube. So it's the same process pretty well every day, and pretty relentless. So after a while you get a bit sick of it, so you have a break, which is a good thing, because then the following day you sort of back to normal. Also, I'm strongly motivated because I tell myself, what are the longer term consequences of what I'm doing? And I'm hoping that other, particularly retired professors, will seriously ask themselves the question that all their knowledge that they've accumulated for decades will just rot when they die. And what a tragedy. And it's not necessary that that happens, because they can easily record it. They can just as easy as I did buy a camcorder and a tripod and a whiteboard or whatever, and just do what I'm doing, and then give their knowledge to humanity, to posterity, to the younger generation and so on, and educate the world for free. So that's a pretty strong vocation, and I hope attractive to a lot of people. So I'm hoping the pioneering effort that I'm making will attract other people to do something similar in, all topics. So that realization, that awareness motivates me to push on, despite how relentless it is. Okay, that's said. Okay, so we're talking about scattering. And we modeled scattering in a fairly simple way, a fairly simple model to start with. We had an incoming wave front, so imagine a plane wave coming in to a target that's very heavy, so no recoil, so the energy in equals the energy out of the particle, the scattered particle, so its de Broglie wavelength remains the same. All these simplifying assumptions, so make the model more soluble, that you can actually solve things. Right, and we assumed that the scattered wave took a spherical form, so hence the ER underneath, and the usual oscillatory form, but now radially, so the scattered wave is sort of imagine like a spherical wave, and modified by a term called, let's see, what was it called again? Scattering amplitude. So this f of theta here, and as theta is just the angle that the particle gets scattered through, right? And so it's coming in along the x-axis or the z-axis, whichever you like, just a label, right? So it comes in and gets deflected, and that deflection angle is theta. And so effectively studying this model is all about finding this function, this scattering amplitude, this f of theta, right? And we ended up getting this equation, and why the sigma? It's a consequence of the fact that the Schrödinger equation is linear. I can remember I've mentioned it once or twice before, I think, but if an equation is linear and you have one solution, let's call it just psi 1, and you have another solution for the same equation, call it psi 2, then if that equation is linear, then the sum, or the weighted sum, say weighted by numbers, so let's say two numbers, alpha and beta. So alpha psi 1 plus beta psi 2, that weighted sum is also a solution. And that's typical of linear equations. And Schrödinger's equation is a linear equation. So here you've got a, it's a solution to the Schrödinger equation, the STI, Schrödinger time independent equation. Here are your numbers, they're your weighting coefficients, if you like, and you're just adding them. And you're not just adding two equations, you're adding, well, probably infinitely many. Okay? So this general form here a solution to the Schrodinger equation. Now we derived that earlier, so I've just written it up here as a bit of a revision. Now remember, this chapter is the last and fourth chapter on the examples of solving the Schrodinger equation, and the theme of this chapter, of course, is scattering. And scattering is a pretty hefty subject. You can go well into graduate level on the theory of scattering. So, I've said in earlier sessions in this particular lecture, this chapter 5 on scattering, there's quite a bit of stuff that is coming down from graduate level, and it's just in a sense thrown at you. So expect more of the same this session. So okay, so ICBST, that hated phrase, it can be shown that. In other words, you're not going to be told why. Well, I'll give you a hand-wavy way, but this term here, you can rewrite it in sort of using these terms, and you may ask why. If you've done any Fourier, F-O-U-R-I-E-R, Fourier analysis, then you may be familiar with what's going on. Basic idea of Fourier analysis, or Fourier series, let's say, is that if you have some function, say some function that's periodic. So let's say it's a function of x, and there'll be some period at x, call it I don't know, big X. So if your function of little x is equal to your function of little x plus big X, where x is, every x the function repeats. So if you have a repetitive or a periodic function, then you can approximate that function by adding sine curves or cosine curves, and that mathematics, that analysis is, well, it's not too difficult. Second or third year undergrad. Now it's I will probably have to do at least a short course on Fourier analysis because it's so important. I'm trying. This whole MPC stuff, math, physics, computing, is supposed to be grad level courses, but I keep adding undergrad courses as prerequisites. But Fourier analysis is pretty important, so I should do at least half a course on that. Anyway, for those of you who know about Fourier analysis, you can do something similar. Instead of using sines or cosines, you can use these Legendre polynomials. So they act a bit like your sines and cosines. So you can add them with coefficients to get some function that you want. Now this is periodic, right? As kz is multiples of 2 pi, you get a repeat. So it's so a la Fourier analysis, you can do something similar with Legendre polynomials. So just assuming that's the case, so it can be shown that this can be written in this rather complicated form, which is just like an infinite sum of weighted, like these are your coefficients, if you like, Legendre polynomials. Okay. Right. So that means that you can. Now here's your wave function. That's your solution to your Schrodinger equation in this context of scattering. It's in this simple model. It's a superposition of two wave functions: the incoming, before the scattering, and the scattered wave function. The incoming wave function and the scattered wave function. Right? And we can rewrite this in terms of Legendre polynomials. Okay. So we put for this instead of this, we can replace it with this. Right? So let's do that. So put all this in here, and then now we have a wave function that's the incoming wave function and the outgoing or scattered wave function, and we've rewritten this in the same in a polynomial form. Okay. Now this u here we eventually got in this form, right? In terms of Legendre polynomials here. All right. So this equation here is your u. In other words, it's the sum of these two terms. So this thing here is the sum of your incoming wave plus your outgoing wave or scattered wave, right? Now, so if you take this sum, I'll call it the sum wave function. You know, this plus this here, the sum wave function. If you subtract from it this term, in other words, this term, which is the same thing, then if you take the sum wave function, subtract from it the incoming wave function, well, what are you left with? Well, of course, just the scattered wave function, this one here. Okay. Now, scattering boils down to analyzing what f is, finding what this scattering amplitude is.